am Mr. True. Well, when you were in your trigonometry class or your pre-calculus class, I hope you didn't think that you'd never see those trig functions again, sine, cosine, tangent, all that good stuff, because they are going to keep coming back over and over again in calculus. So, we've talked about finding limits, graphically, numerically, using the properties of limits, but what we haven't talked about yet is finding limits of trigonometric functions. So, let's see any real number in the domain of the given trig function, and let me just step out here again a little bit while I'm talking, so you can copy the bottom. We have the limit as x approaches c of sine of x is equal to the sine of c. We have the limit as x approaches c of tangent of x equals tangent of c, and so on and so on and so on. Basically what you're looking at with all of these 6 trig functions is that you're going to be able to just simply take the value of c that you're allowing x to approach and simply just plug it into the trig function. The reason why you can do this is, and why it needs to say let c be a real number in the domain of the given trig function, like tangent is undefined at, what, pi over 2, and then plus or minus n pi. Of course, until you mess around with the period and everything. But tangent, secant, cotangent, they all have vertical asymptotes, and thus they all have values at which they're undefined. But within their domain, they are smooth and continuous curves. And smooth and continuous curves, pretty much like your polynomials, as we started to just introduce the properties of limits, curves that are smooth and continuous, there's no sharp bends, there's no holes, there's no vertical asymptotes. Within the domain of those smooth and continuous curves, finding the limit is really, not much more than just taking the value of c that x is approaching and plugging it into the function. Now, there's a lot to, there's a lot of complexity with the idea of limits, but with these smooth and continuous curves within their domain, to find the limit at c, we're lucky enough to just simply be able to plug in those values. We're going to go to the next screen. There's 2 special cases, which I'm going to back up with a couple of graphs, and then do a bunch of examples. Here's our 2 special cases. We have the limit as x approaches 0 of sine of x over x equals 1. Now, the function f... We interrupt this video to inform you that Mr. True cannot copy his notes. I do pre-work all my problems out before I make these videos, and even so, occasionally, I mess up. So I had wrote this as 1 minus cosine x over cosine x, and because I can't talk and think at the same time, as sometimes, I never noticed I made a mistake with this section of this video. So let's try that again. And let's get the 2%, well actually let's make sure I'm right all the time since they're videos and you're trying to learn from them, and there are no mistakes. So, our 2 special trigonometric limits are the limit as x approaches 0 of sine of x over x is equal to 1. If we were to graph with our graphing calculators, then it'd be easier if it's in radian mode. It'll fit in the screen, your graphing calculator screen a little better. Put that in radians and graph y equals sine of x over x. And you'll have a graph that oscillates along the x-axis, but as it gets closer and closer to the x value of 0, which is where we're allowing our limit to approach, it starts to grow in oscillations and get to the biggest oscillation where it reaches a y value, or almost reaches a y value of 1. So, and we have this x-axis acting as an asymptote, except the graph is just oscillating, and every time just a little bit shallower and shallower until you go out to infinity and negative infinity, though of course never, becoming a straight line. It will continue to oscillate around that x-axis. So what is happening? Well, as you approach 0 from the left, and if I were to do a one-sided limit, would have a little negative up here as the exponent. When you approach 0 from the left, the graph is approaching a y value of 1. And if you approach it from the right, it's approaching that same y value of 1. So the left and the right-hand limits are equal and are approaching the value of 1. But we have the hole here, the removable discontinuity at 0, 1, because you cannot divide by 0. Most of the time, when your denominator is equal to 0 and it doesn't factor out, you'll get vertical asymptotes. But indeed, this case, we have a hole at the point of 0, 1, so we would call that a removable discontinuity. And again, the left and right-hand limit are equal to 1. So let's just keep that in mind as we work through our examples after this correction. the limit as x approaches 0 of 1 minus cosine of x over x is equal to 0. And again, it's going to oscillate a little bit differently around the x-axis. It's going to kind of bounce up and just sort of slowly start to decrease the heights of these oscillations and just touch the x-axis as it goes to negative infinity and positive infinity. You can see over here it's above the x-axis, and to the left it is below the x-axis, just touching basically your periods of cosine. At 0, the graph is coming along, it's touching, it's dipping, and it goes through 0, 0. Well, at 0, 0, again, you can't divide by 0. Again, with this particular ratio, we do not get a vertical asymptote at x equals 0. We have a hole. So again, then we have another removable discontinuity as we approach 0 from the left with a little negative exponent. As we approach 0 from the right, and if you're writing your one-sided limits, that'd be a plus up here in the exponent. We are approaching 0 from both the left and the right-hand side, so thus the limit of 1 minus cosine of x over x as x approaches 0 is 0 with that hole right there. And we can see from the graph as well, just to kind of bring in another concept before I let you get back to our regular video, this is an even function. If we take this graph and fold it around the line, not the line, but the y-axis, it will perfectly line up on itself, where you plug in opposite numbers and you get the same answers. F of x is equal to f of negative x. This is an even function. And over here, if we take this function and were to rotate it 180 degrees, except for the labels on our x-axis would be upside down, the graph would line up with itself exactly. You plug in opposite numbers and you get out opposite answers. That is what's going on with your odd functions. F of x is equal to the opposite of f of negative x, or opposite of x. So, even function, just symmetry to the y-axis, odd function, symmetric to the origin, and these two special cases of trigonometric limits that we're going to use as we get through our next, I believe it was 6 examples I did in this video. So, I'm Mr. True, back to our regular program. And let's see how they're used, and I think I'm going to do about 6 or 7 examples, and we'll call this video. Here's the first 2 examples. We have the limit as x approaches pi over 2 of the cotangent of x. Well, cotangent of pi over 2, let's see. We just had that chart up there. It said if I was finding the limit as x approaches c of cotangent of x, that it would just be simply equal to the cotangent of c if this value was within the domain. So, this is going to become the cotangent of pi over 2. Okay, on the unit circle, pi over 2 is 90 degrees, so here's 0, pi over 2 is 90 degrees. Now, cotangent of theta is equal to what? X over y. So at pi over 2 or 90 degrees, the x value is 0, and the y value is 1, and 0 divided by 1 is 0. So there's our answer. The limit is 0. This one, though, I've kind of thrown this in to what would happen if you weren't really thinking about the domain of your trig functions and you were just boom, boom, boom plugging in these numbers. Well, the limit as x approaches pi over 2 of the tangent of x, your issues with domain are going to come from the quadrantal angles. Well, I guess I say that, but of course, if there's some kind of multiple in x, so that changes the period, so maybe just forget what I said. Just plug these in and see what happens. The tangent of x, as x approaches, the limit as x approaches pi over 2. Well, okay, we're just plugging these in, right, or attempting to, and that's going to be the tangent of pi over 2. Now, pi over 2, tangent's y over x. So, y at 90 degrees is 1, and the x value is 0. Well, 1 divided by 0 is undefined. Well, when we solved or found limits using the properties of limits, if we approached a value that made our function undefined, we would find the left and right hand limits and see if they were equal. Well, actually, with algebra, a lot of times we do some manipulation to see if we can just change that denominator or cancel it out altogether. But if the left and right hand limit is equal, then we can say that that is the limit. Now, if you understand what tangent looks like as a graph, you'll understand that the left and right hand limit is not going to be equal. But without drawing a picture, how would you check for the left and right hand limit? Well, let's see. We're going to say, let's let the limit as, well that's nice handwriting, let's let the limit as x approaches pi over 2 from the left of the tangent of x. Again, I'm going to try and explain this without looking at the picture, which you certainly should know what the parent function looks like. You should know what y equals tangent of x looks like. I'll draw it for you in a second. But as you approach pi over 2 from the left, x is less than pi over 2. X is in or next to the trig function, so it has to be an angle measure. So our angle measure is a little bit less than pi over 2. Well, if I'm on the unit circle and not looking at the graph, less than pi over 2 is between 0 and pi over 2, so we're in quadrant 1. Now, when we're in quadrant 1, tangent is positive. And tangent, again, is y over x. And we're in quadrant 1, the y value is approaching 1, the x value is becoming infinitely small, so a very, very small value in the denominator. So this is shooting towards positive infinity. Whereas, if I approach pi over 2 from the right, the limit as x approaches pi over 2 from the right of the tangent of x, and again, out of a trig, you put an angle measure into a trig function and you get out the sides of a triangle, basically, the ratios. And again, we're looking for y over x. As we approach pi over 2 from the right, that means that my values for x are a little bit larger than pi over 2. So that means if I'm more than 90 degrees or more than pi over 2 radians, I'm in quadrant 2. Well, in quadrant 2, my x's are negative and my y's are positive. So when I do that division, I'm going to get a negative answer. So indeed, when x is greater than or approaching pi over 2 from the right, and I'm making my hand motion as if I'm on the unit circle, if my angle measure is just a little bit bigger than pi over 2, then I'm in quadrant 2, and tangent is negative in quadrant 2. So this is going to be negative infinity, and my left and right hand limits are not equal. Thus, my two-sided limit does not exist. That's why in the previous screen I said, as long as c is within the domain of the trig function, then all you have to do is plug in c. Well, pi over 2 is not in the domain of tangent of x, and so that's why we're not getting an answer. And by the way, just to give you a quick sketch, this is y equals tangent of x. Here's our first asymptote at pi over 2. Here as we approach pi over 2 from the left, it's shooting off to positive infinity. And then the second period is going to come down from negative infinity and then continue on. So as I approach pi over 2 from the left, it shoots up to positive infinity. As I approach pi over 2 from the right, it's going down. So we got 5 more examples. All of those, unlike the second one, will have an answer. All right, let's get going. We've got the limit as x approaches 2 of the cosine of pi x over 3. So we should be able to just take the 2 and plug it in. So that becomes the cosine of 2 pi over 3. Did you get that unit circle from pre-calculus? I hope not. I know my students have, and I quizzed them on it to death. The cosine of 2 pi over 3. In case you're a little rusty on the unit circle, pi over 3 radians is equivalent to 60 degrees, so just in case you need that. So let's see here. 1 pi over 3, which is 60 degrees, 2 pi over 3, which is 120 degrees, which lands you in quadrant 2. Not that you should have to mentally flip back and forth between degrees and radians that much. You really need to know that unit circle. The cosine of 2 pi over 3 is negative 1/2. Next example, we have the limit as x approaches 0 of sine of x over 4x. This looks familiar or similar to that one of those special trig function that I brought up, but it has a 4x in the denominator instead of just x. So as you get more comfortable with limits, you might not need to show this work, but we're just learning this, so I got to break it down. Break it down. All right, so it becomes a limit as x approaches 0 of 1/4. I'm going to pull that denominator out, make it a separate factor, times the sine of x over x, that, since we're just learning all these properties of limits, is equal to the limit as x approaches 0 of 1/4 times the limit as x approaches 0 of sine of x over x. Well, when you take the limit of a constant, there you go. When you take the limit of a constant, regardless of what the value of c is, the answer is going to be the constant itself. So the limit as x approaches 0 of 1/4 is 1/4. And the limit as x approaches 0 of sine of x over x, we just saw the graph where they had a hole at the y value of 1. It was coming up and approaching the value of 1 from both sides, so the limit here is equal to 1. And that final answer is 1/4. The limit as x approaches 0 of sine of x times 1 minus cosine of x over x. That doesn't look like what I had up here on the previous two introductory panels either. So, I'm going to do something similar to what I did with number 4, which is I have two factors in the numerator, sine of x times 1 minus cosine of x. So I'm going to pull that multiplication apart. And in the denominator, I just have 1x. Now, it could be x squared, and both factors would have an x in the denominator, but I only have 1. So this is going to be expanded to look like this. The limit as x approaches 0 of sine of x over 1, that's really unnecessary, I'm just doing that for teaching, times the over 1 part, times 1 minus cosine x over x. Now, I have just made this look different. I didn't change its value. Let's see here. Sine times 1 minus cosine x is what I have in my numerator. And 1 times x is just the x. So, I can now take this product and find the limit of each factor within that product and write limit as x approaches 0 of sine of x times the limit as x approaches 0, and I'm running out of room here, of 1 minus cosine x over x. Okay, I did not run out of room. Okay, limit as x approaches 0 of sine of x. 0 radians, sine of x. Sine is y over r on the unit circle, or just the y coordinate. So at 0, the sine of 0 is 0 times the limit as x approaches 0 of 1 minus cosine of x over x is, as we just saw in the previous introductory panel, 0 itself, and 0 times 0 is equal to 0. Bye! 2 more questions or examples. Examples. Limit as x approaches 0 of sine x squared, or sine squared x cosecant x over x. And can't plug in 0 because it makes the denominator undefined. That does not look super easy, but if you remember your trig functions, and if you remember that sine and cosecant are reciprocals on the unit circle, sine of theta is y over r, and cosecant is r over y, they cancel each other out, or they're reciprocals. So, I can rewrite this as, or just take out, just for matters of space, I can rewrite the cosecant of x as 1 over sine x. And then sine squared over 1 times 1 over sine, those are going to cancel out. This sine in the denominator from cosecant, the sine in the denominator is going to cancel out with one of the two signs that are in the numerator, and we end up with the limit as x approaches 0 of sine of x over x, and we now know that that's equal to 1. Next example. The limit as x approaches 0 of the sine of 5x over 2x. Now, this looks very similar to the limit as x approaches 0 of, well, I have it over here. Oh, I have it over here. So why write it again? Looks like this. Sine of x over x is equal to 1. But this is not an exact match to this. Now, I don't really care about the fact that there's a 5 or a 2. What I really care about are these values are not a perfect match. Okay? This is the sine of, this is really the limit as x approaches 0 of the sine of something over the sine of something equals 1. What's important is those somethings are a perfect match. You know, that it's x and x. It's not x and y. It's not a and b. It's the sine of x over x. This is the same variable, so thus they must represent the same value. So what we're going to get here in a minute is I can't change this 5x because it's the sine of 5x. That 5x is within the sine function. So I can't really change it. But what I can have more flexibility over is with the 2. And if I can get the sine of 5x over 5x, if I can get the limit as x approaches 0 of the sine of 5x over 5x, then that will equal 1 just like this is equal to 1. So what I'm going to do is I'm going to expand this out and get the limit as x approaches 0 of, I'm going to take that 2 out of the denominator, and it's 2 times, the denominator is 2 times x, and it's a factor, so I can pull it apart and get 1 over 2 times the sine of 5x over x. Okay, well, whoop-de-doo, I still don't have a match. This is still 5x, and this is still just 1x. And again, this 5x is in the math function. It's not sine times 5 times x. It's the sine of 5x. So that 5 is going nowhere, not without some identity work or something. So forget it. It's not going anywhere. Well, I've pulled the 1/2 out, or pulled the 2 out of the denominator and wrote it as 1/2. And now, if I can do some other kind of manipulation with that multiplication going on there, I'll be happy. Like if I could get that denominator to be 5x, I could be done with this problem. So if I could just make it the limit as x approaches 0 of something over 2, I'm going to add something in, times the sine of 5x over 5x. If I could just get a 5x to be in the denominator, well, I just took that denominator and multiplied the denominator by 5, or I took the sine of 5x over x and divided it by 5. So if I took this and divided it by 5, then I could just simply cancel that out by multiplying by 5. So what I just did there was, I'm not sure if maybe you're totally happy with that, so what I kind of just did here was I came in and I multiplied that second fraction by 5 over 5, and then, with the commutative property, whatever, I moved this 5 over here to be on top of the 2. When I multiply top and bottom by 5, 5 divided by 5 is 1, so I'm just making it look different. I'm multiplying by 1, I'm not changing its value. Well, now this becomes the limit as x approaches 0 of 5 over 2 times the limit as x approaches 0 of the sine of 5x over 5x. This is a constant, so this is 5 over 2. That is equal to 1. So that's equal to 5 over 2. Now, please don't be tempted, even though this pattern has shown up. You could just be going like, well, there's a 5 over 2 and that's your answer. Is that always going to happen? It might. But I would strongly suggest not trying to glance at this and seeing some kind of shortcut and thinking that, that's always going to work, because many years ago when I first took Calc 1, and I was just out of high school, I was working full-time, I had a girlfriend who's now my wife, but lots of distractions, so didn't do quite so hot the first time around in Calc. And that was because I was looking for these shortcuts. I wasn't studying enough, I was working too much, I was tired. So I went into this calc test. It was integration, which we're far away from as far as us explaining it. And I got into that test and I was like, that was so easy. And yeah, it's because I bombed it. You need to get these equations that you're dealing with when you're going to use some kind of like identity, or, well, let's just call it an identity, and pull it in and use it within your math problem. You need to see like an exact match to make that applicable. So looking for shortcut patterns is going to run you into big trouble. So get that algebraic manipulation done. If you're going to use some kind of identity or property, make sure that it is an exact match before you try to apply it. And I explained why the 5x was there, why that was okay, and hopefully understand it. This is my last example for finding limits with trig functions. I'm Mr. True. Now go do your work. Go do your homework.